Okay. I don't have a lot of time left today, so I will talk a little bit about a wave function of a free particle. So free particle means no forces acting on the particle. Okay, so first of all, what does classical free particle do? Okay, what is a classical solution that fully describes the motion of a free particle? Very easy. You would say that velocity equals constant initial velocity. Okay, velocity stays the same, and position, well, it's the initial position plus initial velocity times time. Okay, that's it. You can also describe momentum, which is initial momentum, m times initial velocity. You can also describe the kinetic energy, which is 1/2 p squared over m. So it's a p initial squared over m, which is m squared v naught squared over 2m. So that's just 1/2 m v naught squared. No surprises here. Okay, so that's a full description. Okay, now in quantum mechanics, we discussed that while in the classical regime, the state of a particle is described by its position versus time, so this is equal to x of t. In quantum mechanics, the state of a particle is described by the wave function. It's a function of position and time. The wave function can then be used to predict the probability that if a position measurement is made, then it will, then that position will take on a certain value, right? So the probability of x at time t, is given by, that's a probability distribution, right? So the probability distribution is given by the amplitude square of that wave function. Okay, so this is a probability distribution. And we just discussed that to turn it into a probability, you have to multiply that distribution by dx. Okay, so that p of x dx equals probability of finding, this probability of distribution of position, probability of finding a particle within dx of x at time t, right? So I have to put a time dependence. The probability distribution depends both on time and space. Okay, so that's why I'm writing it like that, because it's a function of two variables, space and time. Anyway, how do I get that wave function? I've been dancing around this topic for a very long time. How do I get that wave function? And the answer is, it's a solution to Schrodinger's equation. In classical mechanics, this is a solution to Newton's equations. You probably don't see it that way, but you could say F equals MA, 0, F is 0, this is MA, A equals 0, so therefore V equals V naught, and therefore X equals X naught plus V naught T. So this really is a solution to Newton's equations. In quantum mechanics, the state is described by the wave function. Okay, so now I'm going to write down the Schrodinger's equation. I'm going to just use this kind of abbreviation for a free particle. Schrodinger's equation will take on a different form if the particle is under the influence of some other forces or some other interactions. So it's a partial differential equation. And at first, you might be scared. You might be unhappy. And then we will learn how to understand what this says. Okay? This is a partial, the left-hand side is a partial derivative of psi with respect to time. There's a partial derivative of psi with respect to x squared. And there's this bunch of constants here. Remember, h bar is h over, oh, sorry, it's h over 2 pi. Okay. M is the mass of a particle. This looks like completely not like anything like this. Okay. Remember, a wave function is a wave. What we seek is we seek a solution psi of x and t given an initial psi x t equals 0. That's the standard philosophy, right? Initial psi might be a very localized peak. I might know where I release the particle, and once I release it, the information about the position of the particle is lost, and the wave function evolves in some way. You already saw examples of wave functions evolving in the simulations 2 days ago, so I wanted to give you a visual so you have a little bit of comfort with this. Now we're doing the math. Now, this equation, and as many partial differential equations, they don't have a single solution. There's a whole multitude of solutions. But I will write down a solution, and we will check that that solution is indeed, it indeed satisfies the wave function. Check that the following plane wave is a solution. So here's the plane wave solution. E to the I, kx minus omega t. We've already had a discussion about this yesterday. You already have a homework on that. So it's like at least the third time that you're seeing this. Now, the first time when you look at it, you would say, well, this looks like an exponential with an I in it. But now you know that this is just really a fancy way of writing down a pair of sinusoidal waves, because this is a cosine kx minus omega t plus I times a sine of kx minus omega t. So your textbook has this interesting visualization. So at t equals 0, it's this corkscrew. So you have a real, imaginary, and the x, and that corkscrew moves. I'm not sure if that really is such a useful way of visualizing. It looks cool, but I'm not sure what that gives us, what that affords us, that kind of thing. Okay. Well, let's see. So check. Partial psi, partial t equals, I'm just going to work with this form. You see, it's much easier to work with complex exponentials. Minus I omega times a e to the I kx minus omega t, which is just minus I omega times the psi itself. Partial psi, partial x. You can see by similar argument, it's going to be ik times the psi. And the partial squared psi, partial x squared, is ik squared times the psi, which is minus k squared times the psi. Okay, so now, so what I see is that I see, looking at this, so let's just substitute that back into here, okay? So I have minus I omega sub into Schrodinger's equation. So on the left-hand side, LHS, I have minus I omega psi. On the right side, RHS. What is it that I have? I have a bunch of IH bar over 2m. I have IH bar over 2m times minus k squared psi. Okay, so then when I sub into the Schrodinger's equation, I have minus I omega psi equals IH bar over 2m is minus k squared psi. I can cancel out the psi. And I can cancel out the I can cancel out the minus. And this says that omega equals h bar k squared over 2m. So this says, yes, plane wave is a, or let's say, can be a solution but only if omega and k are related in this way. Okay, the relationship between frequency and wave number in a wave is called a dispersion relation. Okay, so evidently the wave number and the frequency must be related. Have we seen a dispersion relationship before? We've seen it. For photons, omega equals ck, okay, or f equals c over lambda. So we've seen an example of a dispersion relationship. Okay, in our case, we're dealing with a different type of particle. We're dealing with a massive particle. So it has a different dispersion relationship. Can we make sense of it? Well, this is a plane wave with a single k and a single omega. Here, we have a plane wave with a k and omega. And we discussed that if you have a plane wave with a well-defined k, you have a well-defined momentum. So the momentum equals h bar k, and the energy equals h bar omega. Okay, and what this means is the following. This wave function describes a particle with a well-defined wave number and therefore a well-defined momentum, And at the same time, it has a well-defined angular frequency, and so therefore it has a well-defined energy. And so you will realize that we can rewrite, then if I multiply both sides by h bar, I have h bar omega equals h bar k over 2m. And you say, oh, this is E equals p squared over 2m. And okay, now we brought a little bit of sanity back. This is just a relationship between energy and momentum of a classical free particle. Okay, so if you go back to the classical particle, where is that? It has this relationship right here. Okay, P naught meaning initial momentum, which stays the same as momentum at any time. That's why the naught. That's why there's a subscript P naught meaning initial momentum, but it's the same as momentum at any other time, right? So we have energy equals E squared over 2m, and we found that the same relationship holds true in the quantum domain. Okay, so thus a plane wave describes a particle with a specific momentum and specific energy, and these are related in the way that's the same as for a classical particle. Later, we will learn how to get energy and momenta without using de Broglie relationships, right? So these are de Broglie. Okay, we'll basically derive these relationships. What about the probability distribution? Okay, so a particle is described by this wave function. It's a solution. So here's this wave function. What's wave function good for? Well, for one thing, it gives a probability distribution of a position measurement. How do we get the probability distribution if we have the wave function? Right? It's given like that. And how do you compute that? Well, we discussed that yesterday. You take the wave function, you take its complex conjugate, you multiply the two together, and then you take the square root. Okay, so I have a to the minus I kx minus omega t. This is the psi star. And then you multiply that by the psi itself, e to the I kx minus omega t. You realize that these things cancel. That gives a squared, that's a. Okay, constant probability distribution. And what that means is that if you make a measurement, you're equally likely to find the particle anywhere in space. Now, there's a lot more that I can say, but I think that will get you started. This is enough for you to do the homework. This is a lot of information, very new stuff, strange things, Schrodinger's equations, complex numbers, probabilities. Well, this is the simplest example, free particle. And then we will continue to weave this tapestry thread by thread. I'm trying to be very systematic. I'm trying to give you what you need before you actually can use it. So I think I gave you what you need this weekend. Now go ahead, do the homework, do the wave lab, You have a couple of problems about the wave function that will get you started, and then we'll continue next week. Okay, have a good weekend. Please take some break.